Okay, well, it's a good idea to talk today about aggregate packing and importance of aggregate optimization. And this talk is by me, my collaborators Adil and Iman, and also AI copilot. So when we discussed about using evolutionary algorithms and AI, I just thought like, okay, let me try something new. And so I decided to use AI to create a presentation, and it really worked well. It also helped me to create some script. So the partially script, of course, from my paper was created by the AI. And the idea of dense packing comes from, for example, Kepler, and he was discussing the packing of cannonballs, equally sized spheres, but even earlier, Apollonian, he was working on packing of disks, and he created these problems which we still try to understand and model better. Okay, mathematically, we can solve the problem for ideal packings of ideal disks and ideal spheres. And, well, the real world is a little bit different. So most of the time, we may need to deal with random Apollonian packings, which are not really perfect arrangements. And again, this is where we can use our algorithms, which can mimic nature and natural formations. And this can be used for concrete packing and understanding concrete packing and importance, again, and correlated to concrete properties. So the important is very clear, because we try to optimize the packing, and we really, our objective is to see if we can have a better strength, or we can save some amounts of binders. So Portland cement can be easily saved. So this is an example from our project which we did with DOT, with my students and in my lab. So basically we optimized 3 aggregates, and we analyzed the packing density. And yes, the higher strength values they do correspond to better packing arrangement. So, well, we like to put it in this ternary diagram, and we realize that where is the densest packings are here, for example. Again, this is not a very common case, because we had relatively large sand, so the optimal mixtures, they were really requiring high sand contents. But the optimal strength values which we obtained are really here, in this circle or ellipse and ellipsoid, and where we have the packings are there. So basically, there is still, I would say, the gap between the optimal packing and optimal and higher strength values. So it's not really exactly the same, but obviously the pushing for better packing obviously sends us into right direction. And so again, I just decided to look for the optimal solution, and so I decided, okay, let's ask ChatGPT to create a code for aggregates packing. Well, it succeeded with 123 lines of code, and the code is well, relatively simple, I would say, and it gave like some explanations, which was very useful to understand what's going on. And basically, the code is capable of doing some packing work, but really with some limitations. So 100 spheres were packed, but unfortunately, it cannot do like better with all larger spheres. So again, it was a good step, I would say, but if I would give my students such an assignment, it would be C-, because it really doesn't show me what I want. So if we look for any AI techniques which are there available, so artificial neural networks, which were very popular back in, I think, in 90s, Now they are coming back as major engine of AI. Basically, the mechanism is to use the data set and use a neural network a model which can be, I have next picture explaining it, so which can go through the range of the training and optimization of the model. It can create a equation, and basically you have, depending on the configuration of neural networks, number of the nodes, depending on the weight coefficients, and very often weight coefficients are not reported in the literature, it can really represent your training set, and you can also, after that, you can go and analyze it using your data set. Question is, again, for this you need a very comprehensive data set which you can analyze and convert into the model. So, okay, artificial neural networks can create perfect models of reality which we have, and it can mimic all the noise, all the deviations you may have, but it is not really, so far I didn't see that it is used to work on basic relationships we have already established for concrete technology. So what are other different techniques? Should not be only an N there to deal with. And we really look for genetic algorithms. Genetic algorithms are another approach which we can use to optimize the system, and we can use it to solve sophisticated numerical problems. For example, we used a genetic algorithm in the past to find optimal aggregates, to provide us aggregate selection for the ready-mix manufacturer when we had 25 to 10 to 15, etc., different potential aggregate sources. And with genetic algorithm, we were quickly solving and suggesting which sources to use based on different criteria. So basically, we look for genetic algorithm, and genetic algorithm can be really used to optimize concrete mix, but you need to have a model, and it's powerful optimization mechanism. We improved it further with shifting and shrinking mechanism to optimize the solution and basically to find solution quicker. So comparing to classical genetic algorithms, we can have a better realization and better solution. Obviously, the major problem, if you have different maxima to find in equation, this tool can be effectively used. So very powerful tool which can be used to solve numerical problem. But question is, you need equation, you need to model to solve if you want to use genetic algorithm. So I'm returning back to my work on sequential packing algorithm, shortly called SPA, and this was the model, two-dimensional model, which I demonstrated before. So basically, the algorithm is more complex comparing to this ChatGPT 123 lines of code. But the idea from ChatGPT is we realize similar idea, but we have ability really to arrange the particles in the way we like to arrange. So if we like to create random Apollonian packings, which extremely dense arrangements, we can really create them. And of course, 3D, we're not interested just in 2D, 3D implementation is there. And we have normally, in addition to number of packed spheres, we have 4 key parameters defining the algorithm run. Well, what we can do, we can also demonstrate that the packing of like only coarse aggregate fractions, which again, everything here is modeled as spheres. But we also can model very large assemblies. I think from 1 to 20 million of particles is possible, and it is basically the number of coarse and fine aggregates in container, 1 liter container, 1/4 container, say. And so Mother Nature can be really modeled in a relatively realistic way. Well, I will speak more about features of algorithm but here I really like to mention that we can have extremely dense packings to create. And again, I don't want to spend time on the flow chart. Someone told me this is very old school, but question is, it really understands, yes, it was not ChatGPT created in ChatGPT, it was from my paper, and again, but it helps engineers to understand the logic, and it's easy for us to explain. So, but what we did also to run the algorithm, because all the packing happens in memory of computers. So we don't record every pack data into the file. And for this reason, we need to optimize the way how computer works, the way data are questioned by the algorithm. And for this reason, we created different separations, different divided packed volume into smaller spaces, especially which helps us to pack very small aggregate particulate entities. And so multi-cell is very effective packing, very effective packing approach. So as a result, we realized very dense theoretical packings, again, theoretical packings of aggregates, which are exceeding all our available packing curves. For example, DIN has 1045 has this packing curves A, B, and C, and also gap gradient. We understand that gap gradings are not something we like in concrete technology. Sometimes they work, but most of the time we try to stay away from them. So if you look for this gap gradient and this very dense simulation curve, they are somehow close to each other. We understand this dense packing of aggregates most probably is not going to work in concrete. But there are some other simulations which I have here. They are might be very useful for concrete technology. And I'll return back to this arrangements with next slides. So again, very dense packings. But what I like to say, there's dense packings, theoretical packings again. They are achieved with relatively large, I would say at least maybe 50% of maximum, very close to maximum size. So again, practical advice, if you want to optimize your aggregate packing tomorrow, just have significant portion of aggregate of relatively narrow size close to your D maximum. This will really help. And question is, this can be tested. So what's next? Well, genetic algorithm, how it can really help us. So with, if you have this pre-packed assembly, and again, our algorithm is very good to capture the different patterns from very dense to very loose. And I will speak about loose arrangement a little bit later. But if you want to push it further again, if you want to have a perfect fit of the particles, so genetic algorithm works in such a way that you create still a sphere somewhere within free space, and after number of iterations, the aggregate will move around and grow and fill this available void, packing it in a perfect shape. So in addition to power of algorithm which we have, genetic algorithm can match the performance of SAP and enhance it, actually have a synergy, again, if we want to have extremely dense packing arrangements. A question is, again, if we want to compare, you can see this is like our classical SPA, and this is SPA with genetic algorithm. All of this, so again, very dense curves. They are on your right. They are deeper, and the more loose arrangements, they are on your left and upper, and you can see genetic algorithm pushes all of them to, you know, one single master curve, and this is the curve is your theoretical maximum possible density curve for spheres. And can we do better? Well, potentially we can, if we push it further, maybe it can shift a little bit right. And question is, this is how we can define the best packing in terms of spheres. And again, what we discussed with you, that most probably this is not what is happening. So again, if I put it on the DIN 1045 chart, you have A, B, and C curves, and these very dense packings are not really happening. So the question is, really, do we have the best packings in concrete? Do we need best packings, theoretical packings in concrete? So this is a question here. And if we look for aggregate suspension mixture proportioning from ACI 211, we really recognize that the particle separation takes place, and we need to take account particle separation, and we need to take account rheology of the mix. So again, we like to make this correlation of the best packing arrangements. And yes, this is what we achieve with our compaction methods. But again, we need to understand that those are not the best theoretically possible packing arrangements as predicted by the models. So here we need to understand the gap between the packing, theoretical packing, maximum possible packing, and what we can do with our aggregates, how we can move into the assemblies. So this is why we created SPA with separation, and we created particle suspension model. So now we can create the spacings, the gaps between the aggregates, and so we can come with so the cement paste can really come into the play, and you can model now not just simply aggregate assemblies, but aggregate plus paste arrangements. And again, now from these extremely dense arrangements, which are impossible to achieve in concrete technology, we come to something which is we use every day, and which are really not the densest possible arrangements of the particles, but very practical. This is something what we use again every day. So if we look for, again, use of this algorithm, you can, those are practical blends which we created for the project, which were the best for the particle size distributions, and those were the models running to achieve very similar gradings. I mean, similar in terms of close to the power curves. And this was the experiment we run, and again, optimized algorithm can run now into the cycle to match actually the best the specified particle size distribution curve. It can be power curve, it can be any realistic curve, so we can model what we really used in concrete. So can we do better? I always get question, okay, you play with spheres, real aggregates are not spheres, and we've seen from previous slides they really have all the varieties. Well, we need to understand, if I want to model packing of each individual particle as we use in concrete technology, it will require exceptional computational power, and the question is, we can still do it. There are approaches it, but I can just show that, well, we can, the closest approximation can be packing of ellipsoids. We can also run it. It just really requires more computational power and will be difficult for us to push for 20 million as we have for spheres. We can also do fibers. We can do nice packings of fibers and using very similar approach, which can be really done. And the idea is, again, the algorithm which we have can really push the boundaries, model something which theoretically possible but not practically achievable, but we also can use the same algorithm to model what we have in our concrete technology. Here again, I was supposed to talk about AI. We still, AI is in very initial stage, and hunt is for the proper data set, proper input into the AI. I believe that we need to have to verify our models, and those models has to be incorporated with AI, with our computational methods which we have available in our toolbox. In this way we can succeed. And this is basically my main message today. And again, slides created by AI, so you have a little bit weird appearance here, and I think it was coming from Portuguese. And well, if there is any questions. I also like to mention LOGA about CAN, Concrete Advancement Network. This is a new NSF IUCRC center we created together with Oregon State University, with collaborators from Arizona State and UT Arlington. So this is a new center just started, and we had our first industry meeting just a month and a half ago. So we are up and running. And if you need more information, it's very simple, uwm.edu/can, and you will get to some information. Website is still under construction, but we'll have more information about what we are doing pretty soon. Okay, thank you.